And so what we saw is that there's a structure, that there's a tool named a tree, right? That's a diagram that can help us count things. And usually you start in the left, you branch it to the right, and each branch shows you options or possibilities. And the path to kind of go through are the sequence of choices you've made. Okay? So we saw an example of a generic, whatever, random tree of characters. But we actually started studying in more details how to set up trees to work with sets. Okay, and the way we do it is we start with you have to think of the tree as starting in the root node being the universal set, okay? And then each branch is a decision of whether you want to be inside the set or not. So for example, you start in the universal set, then you can be in A or not in A, right? Then if you're sitting in A, you can be in B or not in B. So each layer of decision, each layer of, or each kind of branch that you open is a decision whether you want to be inside or outside of a particular set. Okay? And if you think about it, if you look at a path, if you select like a path, you are actually selecting elements that are inside this intersection, right? So, for example, this path that I highlighted, you are inside set A and also in B, right? Because first of all, you decided to be inside A, then inside B, right? Wherever B is. All right, wherever B is, you're inside A and B. Then you're not inside C, so I'm not sure where C is, but I'm not inside C, so I'm just here, right? And then I'm not in D. Again, just this is too much for a Venn diagram, but I just want to show you that the sequence, right, is the intersection between the sets. So A inter B, inter not in C, inter not in D. Okay? Venn diagrams, when you put more than 3, they kind of get complicated, and that's why we will use trees. Okay? So that's the intersection part. Again, if you take if an example, this red part, you have A, not in A, B, and C. So if you're sitting here, you are an element of this set, okay? And we saw how to use this tool to represent unions, okay? If you want to represent an intersection, if you want to build a tree to represent an intersection, you just do the path, right? Whatever the intersection is. What about unions? Well, unions are, it's representing options. So if you think about this red part here, you have what you're saying with the union is that either the path, the first path works, or the second path works. So it's an or statement. It's a union, meaning that this set works for me. Being here, sitting here works for me, and sitting here also works for me. So when you see this highlight in the tree, you're kind of representing a union operation. Okay? So we stopped here, and we actually draw a tree regarding a taco order right? Where we ordered a taco with chicken, represented by C, with guacamole, represented by G, rice, or rice R, and corn. And you can see that just by stating the tree, we can count the possibilities. So I know in the end of the day that we have 18 possibilities of different tacos, right? 16 possibilities. And I can kind of just assess which taco I've ordered just going through the path. For example, this path here, I know it's a strange path, but it's possible. Somebody ordered a taco with no chicken, no guacamole, no rice, and no corn. So just the shell, right? So it's a strange person, but it can happen. The probability of this happening is it's not, high. So that's why you can see now. You can start seeing now what this is going to study probabilities in the future. Okay. All right. So now I'm going to go back one slide here, and I'm going to prove you one of the formulas that I did not prove before. So there was a formula in week 1 slide that stated this, that this set here is equal to this, okay? This was a formula. And I said, oh no, we're not going to prove this now. I'm going to prove this like in the next lecture, okay? So here the time has come, okay? So why is the left-hand side here of this equation, why this part here is equal to the set A? Well, by doing Venn diagrams, you can also kind of predict that this will happen. But by drawing the trees, this is actually very straightforward. Think about it. If you're inside a universe and then you're inside set A, so you're sitting here means you are inside set A, okay? Now, there are two options inside set A. You can be either sitting inside set B or not inside set B, right? Okay? Now, if I take one way or the other, I am sitting in set A, right? So this, for set A, there are only two possibilities, sitting in B or not sitting in B. If I take both, it doesn't matter what B is, I'm sitting in A, right? So this is a proof that this formula here holds, right? So if I'm taking this way or this way, right? If I get both ways, in the end of the day, I'm sitting in set A, okay? And the formula of the number of elements is also holds, okay? So the number of elements in, the number of elements here, because the sets are the same, this is the same, okay? So this is just a way to prove, okay, that formula. Cool? So if you're sitting in a set and you're kind of wondering where to go next, you just have two possibilities. Considering a next set, you either will go and be in the next set, or you won't. And this will kind of state to you that you're in the set anyway. You can go for the other one or not, but you're still in A. Okay? All right. So now so this is just a recap and the proof, right? Now we are going to, let's get going, and we're going to see some properties of this sets, okay? So again, like, for example, whole sets are just this is one of the properties, okay? So this is one of the properties. And the property is this: a whole set, it could be A, it could be B complement, whatever, are just the collection of all the paths that you pass through the nodes, right? So again, if you think about just having, let me draw it here. Thinking about just what set A represents, set A, like the whole set A, represents the collection of all the paths that passes through A, right? So if you want to represent set A, you would have to do this union here. You would have to kind of say, okay, I'm standing in A, and I have options after. I can be either in B or not in B, and then C or not in C. But whatever option I make, A is represented by all the sum, by all these possibilities of choices, of subsequent choices, okay? Now let's say, how can I represent, so this in yellow, here in yellow, represents set A. Now what about, let's say, let's represent B complement. So let's represent, now I want to represent B complement. And I'm going to do in blue. So to represent B complement, again, the whole set is the sum of the paths that passes through the set. Where do I have B complement? Well, I have a B complement here, and I have a B complement there. So again, it's the sum of all paths that passes through the set. So do you agree that this blue path passes through B complement here? Right? So let me just write this a little bit. It's not visible. So this path here passes through B complement. Is it enough to represent B complement? No, right? Because I have another B complement that's sitting here and nobody passed through it. So this guy also needs to be accounted for. If I want to represent B complement, the blue, like the sum or the union of all blue paths represents B complement, okay? While the yellow, the sum or the union of the paths in yellow, the sum or the union in yellow represents set A. Okay? Questions? Good? All right. So I'm going to skip the trees and subsets for now, although it's not, we're going to go back just really quick. But now I'm going to, oh no, let's do it first. Okay. So let's think about trees and subsets. We, in the first lectures, we asked questions such as, oh, is A a subset of B, right? Meaning that if A is totally contained in B, then A is a subset. Okay? Cool. Now, we can actually test these things with the tree. Okay? What we did in the past was we found the subsets, like, oh, elements A, B, C are in set A, elements B, C, D are in set B, so, you know, like, is one all contained in the other? Now we don't need to do that anymore, like seeing the, like collecting the elements and working out the elements, even because, like, you can have big sets that they're hard to kind of count. So one way to do is to build trees. For example, let's say this question here. Let's say that I have 3 sets in my universe, And I'm asking, is A inter B inter C a subset of this guy here? Right? Which is you have this new set, which is a result of an intersection, united with this set, which is a result of another intersection. Okay? So is this in the left a subset or contained in this great kind of overloaded set here? So if we had the elements, we could, and it's a simple or reduced number of elements that we could list. We could do it, but the other thing you can do is just kind of come up with the tree. Just work, like state the tree, two trees. Try to find who is the set in the left, and then in the tree. So here we're going to state the left set, or the set in the left. We'll state set in the left, and here we're going to state the set in the right. Okay, so who is the set in the left? It's A intersection B. Okay, so we draw the tree. We start drawing the tree like we start from the root. We have three sets, so it's, you know that we'll have three decisions, right? Decision of being in A or not in A, then decision of being in B or not in B, and then the decision of being C or not in C. Okay? This is the way you kind of draw the tree. And then you will select the sets. You're going to state the sets. Well, let's highlight the set here in, let me see, in yellow here. It's A intersection B intersection C. So if you think about the path you're going, you've decided to be inside A, and then you decided to be inside B, and then you decided to be inside C. Set C, sorry. So this, if you think about, if you're sitting here, you're sitting inside of that set. You're an element of the set, of the yellow set. Okay. So this is the path that represents this set. Now let's think about the set on the right. Okay, where is it? My blue marker. All right. So the set in the right actually has a union, right? A union of a blue thing with a pink thing. So if there's a union, I will have to highlight more than one path, right? Because like it's one or the other. Okay. So let's have the blue path first. The blue path first means that I'm taking A inter B. Okay? So let's go with the blue thing and highlight A and then B. Is this all? Should I stop here? How can I represent A inter B? I have to highlight all the paths that passes through B, to A and then B, right? So I should continue to kind of get all the paths, okay? So this is this represents A intersection B for me. Oh, but why? Well, it doesn't matter if I take this route or this route. A inter B is like it's the union of these two routes here, right? So I have to highlight both of these routes, meaning it works for me, either one of them, okay? And then we have the pink part, which is, well, it's B complement intersection C, okay? So first of all, let's start highlighting the B complement. So let's do it from scratch. Let's start highlighting B complement. I have a B complement here, okay? And I have a B complement here, right? But I'm not taking just that. I'm not stopping that there, meaning that I could have both paths working for me after that. I'm actually just taking one path, meaning that I'm choosing to be only in C because it's B complement intersection C. So I have this first path as an option, and then the second path here as an option 2. Okay? All right. So what is the union of this thing? It's just take all the paths. So everything that it's blue or pink works for me. Okay? So to know if you are a subset, you just see if the yellow is highlighted, if the part in the left, which is highlighted in the left, is also highlighted in the right. So does A intersection B intersection C, is this set highlighted here? Well, yes, A intersection B intersection C is actually highlighted here in the blue part, meaning that, well, if blue or pink is good for me, actually the yellow is also good for me. So the yellow is part of the right graph. The yellow is contained in the graph to the right. Okay? So we have a subset. Okay? Questions? We're good? Did you guys understand the OR here? For example, for the blue and pink parts, like it doesn't matter if you're in the blue route or in the pink route, both of them work for you. So you leave the graph highlighted this way, right? And in particular, like each one of them has a path, right? The blue path means A and B. So every path that passes through A and B. And this one, all the paths that passes through B complement and C. So it passes through B complement and C. It passes through B complement and C. Okay, cool? Good? All right. So this is all we need to know to kind of start counting things. Okay? If we structure trees in this way, where the decisions are questions or sequence of where the element is, if it's in a set or in the other set, and then in the subsequent decision you're making the same question for another set, we can start counting things by using what we call the counting tree. And the counting tree is just leveraging this tree structure and putting numbers into it. Okay? So the way counting tree works is this. The number of elements in a set will be represented in the branch. Okay? In the branch coming to the left. So remember, this is the universe, right? The universal set is the root node. If you branch here to the right, meaning that you are in A, I can represent the number of elements in A here in this branch. In this case, I'm giving you like 100. So if you see a tree where you have number 100 here, it means that inside the set A, I have 100 elements. Okay? I have 100 elements. For example, now, and we can go further on steps in the tree. We have, for example, the number. I'm saying you that the number of elements in A inter B is 80. Well, if I'm in A here, my subsequent decision is to be in B. This is A inter B, right? So I will represent in my branch this. This is 80. So if you see a tree where this is 80, it doesn't mean that B has 80. No. Take the path. It means that being in A and in B has 80. Okay? So and you can go on. So for example, let's do this one. Where should I put the number? Oops. Where should I put the number of elements in A inter B complement? So I have to be in A, right? And I also have to be, so here's my A, if you take a look at my mouse there. And then I have to be in B complement. So whatever number I'm looking for, I will state it here. Okay? And it turns out that I already know this number, although it wasn't given to me, because counting trees has cool properties, and one of the properties is that whatever is coming to a node will have to get out of the node. So if 100 elements are coming in A, and I have 80 being in A and B, well, then only 20 will be on A and B complement. Okay? And again, this kind of proves that the set A is actually whatever path you take, right? It's 80 or 20, meaning like you can either be in A and B or A and not B. Okay? So let's go through all the properties, because this property is just one. There are 4 different properties, actually 3, but we stated as 4. And after we have these 4 properties, then we can start doing counting problems. Okay. So here are the 4 properties, and we're going to go one by one. Okay. So let's start with number 1, where we say that the sum of all the branches coming out of the right side of a node equals to the value on the left branch leading into the node. It's exactly what we talked about, right? So let's say here, let's look at this node. If you have 20 coming in, you need to have 20 coming out. Nothing no elements kind of came from nowhere, right? So if you have 12 here in the A complement intersection B complement, which is this branch, what number should I have in the other branch? 8. Okay? Why? Because 20 must be the result of whatever's coming out of this node. Okay? Whatever's coming in needs to come out. So 20 is equal to 8 plus 12. And do anyone wants to try this? What set is this here that I'm pointing to? Who wants to try? No one? Come on. Yeah?
Okay, is it A complement intersect B?
Yeah. This is A complement intersect B, because if you think about the sequence of decisions, I decided not being in A and then being in B. And actually, I can now know that the number of elements of this set is 8, just by using the tree. Okay? Questions on the first rule? Good? All right. Then we have a second rule that states like this. The size of a set is equal to the sum of all branches leading into or coming from the left of the node with that set as the node's name. Okay. What are you talking about? What I'm talking about is this. You take all branches that comes into B, let's say B complement. So what are the branches that are getting into B complement? This 7 here, right? This is this and this, okay? So what's the size of B complement? Well, the size of the set is equal to the sum of these branches. So if I want to know the size of B complement, I'm going to take 7 plus 12, meaning that I have 19. And why is that the case? Well, think about it. You can be in A and be in complement, meaning that you are in B complement. Or you cannot be in A and be in B complement, meaning that you're still being in B complement here, right? Although you're not in A. So A is kind of just it's just where you started off, but in both of these branches you are in B complement. So if you have some people here and some people here, you have to account for all of them. Okay? And you will see that this is practice, and we're going to do lots of exercises, and these rules will kind of sink in, hopefully for you, and it will be like natural to think about those things. Okay? This is the third rule, which is actually the first rule. It's just I don't know why they state this way, but we know that the size of the universal set is the sum of the branches coming out, which is the rule of the whatever comes in has to come out, right? So if 30 plus 20 is coming out of the root node, how many elements I have in the universe? Well, 50, right? Because 30, whatever is coming in the node has to get out of the node. Cool? So this is the third questions about this. I think this is kind of just a consequence of the first one. Okay. All right, and the last one, I would say that's the it's not complicated, but it's not that easy to understand the wording. Is this: the size of a set is equal to the sum of the rightmost values of all the paths that are subset of that set. Okay. So if you think about and read it really carefully, you can take some time to do that, but I'm going to already explain it to you. What we're talking here is that, for example, let's take A, B, and then C, and A, B complement, and then C, right? So if you think about, I'm referring here, I'm not referring to all sets C, because I have some C here that I don't know. If I want to know the size of set C, I should kind of sum all these things together, all these branches together. But what I can say is that A inter B inter C, which is this first path, is 4, and that A inter B complement C is this, 15. It's this, okay? What I'm telling you is that the union of these guys is 15. Now think about this. I'm in A, B or C, B and C, A, not B and C. In the end of the day, whether I'm in B or not in B doesn't matter, right? I'm telling you that I'm in A and I'm in C for sure. I have two paths to be in A and C at the same time. I don't care what path I'm kind of going through. What I know is that I have 4 elements in A and C and 11 elements in A and C. So I have to sum them together to have A and C. So you kind of bypass the middle step, right? So the number of A and C is equal to 15. Okay? This is what I'm talking about, the rightmost subset of everything. It's just like if you have like an intersection that it's clear, A and C, no matter what the middle step is, just sum this value so that you have the number of elements in the set. Okay, this one's a little bit more complicated, but it's not that, we will practice. Okay? All right, so here's the practice. Let's do an exercise. I'll give you guys 5 minutes to try to master this doing a tree, okay? So here's the problem. The universal set is the whole numbers from 1 to 10, the set of whole numbers from 1 to 10. Let E be the set of even numbers, and T be the set of multiples of 3. 3. Make a counting tree, okay, 3 and tree, okay, that shows the possible categories an element of the universal set could fall into based on the sets E and T. Okay? So what I'm asking is, make a tree, okay? Make a tree, represent E and T, represent the sets that I'm kind of describing to you, okay? And kind of complete them with the numbers. Do a counting tree, like put the numbers in the tree. Okay? So again, just to give you a hint, start with the universe. So with the universal set is the whole numbers from 1 to 10. Okay? So you can even represent this because just it's very it's a very small set. So if you want to use like the representations aside just to guide you, you can. State who is E. E is the even numbers. So this ones. And T are the multiple of 3. 3, 6, 9. Now make a counting tree, okay, that show the possible category that the number can. Okay. So this is the set is showing the possible categories these elements can have. Well, I mean, it's a counting set, so the structure of the counting set is always like this. You first branch in a first decision regarding a set, right? So we come out from the root node, and the first layer is a question regarding if we're inside a set or not. Let's take E as the first set that we're considering. So is the set of whole numbers from 1 to 10, is an element even or not? This is the first kind of question, okay? Then you will skip automatically to the next layer, to the next branching layer, right? And the next branching layer, we will be asking a question about the other set that we have, which is it multiple of 3 or not? Okay? So it doesn't matter if you're sitting in the even set. If your element is even, it could still be multiple of 3 or not. And you can have an odd number, you can have a not even number, and still be like this. Okay. And again, this is the structure of counting trees to set up for sets. Okay? It's these layers of decisions of these sets that we are kind of analyzing. I saw some people, while I was walking, do something like this. Universe, then branching in E, not E, and other number. Like, for example, number 1, right? This is a valid tree, but it's not a counting tree. It's not set up in the way that we need to set up to count. Because if we do this, right, if here in this first layer of decision, it was like E, it was like this, sorry, E. meaning that here you're branching in the decision of whether your number is even, multiple of tree, or other numbers. Kind of you can do this tree, but this tree won't hold the properties. The like whatever comes in this node is whatever gets out. This is not valid in this tree, okay? Because it doesn't have this structure of branching on single questions of nodes, okay? Of sets. All right. So after kind of getting the categories, okay? So the tree set up to sets is fine. This is the structure, and you're getting the categories, right? So you can have an even number that is multiple of 3, for example 6, right? This is where 6 sits. You can have a not even number or odd number that is multiple of 3, for example 3, 9. Anyways, you have the categories, but you didn't put the numbers. And to have a counting tree, we need to put the numbers on the branches. Okay? So in our universe, how many elements I have? Well, you can count. It's a fairly small list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, right? 10. Right? Then from this 10, you will have to, like, what's here? What should be here? What am I talking about when I branch here? This number that will appear will be the number of even numbers from the universe. Okay, kind of I'm inside the universe and I'm even. So what are the even numbers? Well, they're stated here. 1, 2, 3, 4, 5. I have 5 even numbers. Okay. What about, okay, I could come here and say, okay, let me find a number of not even. Do I need to? What rule should I use to get this number here of not even numbers? That the sum of whatever's coming out needs to be equal to whatever's coming in, right? So what number should I put here? 5, right? Because the 10 that comes in kinds of have the sum of what's coming out has to equal what's coming in. And it's true, right? You can list it. You can list the even numbers. Okay? There are 5 as well, so it makes sense. But you don't need to. Like, you don't need to do this. You can look at the tree and just kind of get this number just using the rule. Okay? Okay. Now, within the even number, so I'm here, I'm an even number, I'm an element of the even number. How many elements of the even number are multiple of 3? Just 1, right? Which one? 6, right? So this guy here, this number here is even and multiple of 3. So this guy, this number is 1. So what, if you think about the path, I'm saying that I have 5 evens, and then one of them is even and multiple of 3. Okay? Do I need to go and check the, like, do I need to go and check who's T complement? Who's inside the even number that it's not a multiple of 3? Or could I just use one of the rules? Just the rules, right? So I know that 4 will have, will not be multiple of 3. Okay, because 1 plus 4 needs to sum up to 5. Okay? All right. What about here? I'm not in the even number. Okay? And so I'm not in the even number. So I'm talking about this guy's in purple. And I want to know which ones are multiple of 3. How many are there? This is a multiple of 3, and this is a multiple of 3, right? So I have 2. And I'm not even kind of thinking about, I'm just using this rule here that this should be 3. Okay? And you can check it if you want to think about it. The other ones that kinds of that I didn't highlight here, 1, 2, 3, are the ones that are not multiple of 3. Okay? So this is the counting tree that we have as a result. And let's use another rule here. I'm asking you, what are the number of numbers that are not multiple of 3? Okay? So let's say that, just let me just do something here. I'm covering this up, okay, so that we don't count. What is the number? What's the number of t complement? Yep. 7. Let's see. Yes, correct. Why?
You subtract everything that's not multiplication of 3, which is 3, 6, and 9.
Yeah, so you're kind of counting, like you're counting looking at the elements. But let's say that, okay, this is a easy like problem. But let's say that it's too big, like there are many elements and you cannot see this, right? How could you say that it's 7?
Just count the 4 and then do it in a cheat sheet.
Use the rule where a set, you can represent a set or the number of elements in a set by the paths that passes through it. What's the path that passes through t complement? This one? Do we have another one? Yes, where? Here. So this plus this is t complement. Okay? Of course, if you get, rid of the where is it? Of this thing, you can go and exactly do your reasoning, which is correct. But I just want to let you know that if you cannot see the elements, the counting tree, because of the way the rules, the properties work, kind of gives you all that you need. You don't need to look at the elements, okay? So here we use 3 of the 4 rules, and I would say that's actually what we're going to use. That crazy 4th rule that you skip the middle is not that important, at least not for this course. But you use the universal set rule, right? That 10 has to be equal to 5 plus 5. You used the whatever comes to the left of a node has to be equal to whatever goes out of the node to the right. So 5 is equal to 1 plus 4, and 5 is equal to 2 plus 3. And now also you use the rule where if you want to count the elements of a set, just highlight and count the paths that passes through that element, through that set. Okay? Questions? Good? Fantastic. Okay. Well, it was done already here. I'll just get rid of this slide. But I have the new one. All right. Another exercise. 5 more minutes. I want to know, and this is an example where you don't see the elements. I'm telling you that I have a universal set with subsets A and B. And I know the number of elements in the universe. There are 30. I know the number of elements in set A. And I know like a path, an union path there. You have to find it. That's 12. Determine how many elements are in another path. Okay? So I'm not giving you something that you can see the elements. I just want you to use the rules of the counting tree. Okay? So I'm going to leave you guys for 5 minutes trying to solve this puzzle.
Yes, then branching in, yeah. That's it. Ouch.
All right, let's try to solve this together. So I start with the universal set. I know that I have two subsets, so I will only have 2 layers of decisions. First layer, if whether I'm in A or not, and the second layer, whether I'm in B or not. Okay? This is only 2 sets, so it's kind of easy to kind of just use the Venn diagrams, although I really prefer the trees. Even for small sets, I prefer the trees. You can be in A and in B, or A and not in B. You can be just in B and not in A, and this here, if you have a universe like this. Not in A and not in B, meaning you're here. Okay, so this is like I depict all the regions of my Venn diagram in just this small tree here. Okay, so what I'm telling you is that I know that I have 30 elements in the universe. I have 20 in set A. Where should this 20 go? Should it go here? Here? Yeah. Okay. And I know that A complement union B complement is 12. Okay? All right. When you see a union in your tree, you should stop and think, I must have more than one path highlighted. So let's think about the paths here, okay? So let's highlight the path of a complement. A set is the collection of paths that passes through it. So this is the A complement collection of paths that passes through it. Right? I have two paths passing through A complement. Now, what about this blue here, which is B complement? Well, a set is the collection of paths that passes through it. Which paths pass through B complement? This, okay, is one of the paths passing through B complement, all right? And this is one of the paths passing through B complement, okay? So actually, what I mean is that the sum of all of this, okay, the sum of either the pink paths or the blue paths, the sum of the number has to be 12. So whatever I have here, here, or here has to be 12. Okay? So if I call this x, y, z, x plus y plus z needs to be 12. Okay? Then there's the question is this: what is the number of elements in A inter B complement? So it's A inter B complement is actually, I want to know x, right? A inter B complement, it's exactly what I am kind of putting here in the first blue path. Okay? All right. So let's think about the rules. First of all, the first rule is easy. Think about the universe. Do I have the number of nodes in the universe? Number of elements? Yeah, I have 30. Well, only 20 came out of it. So how much should I put it here? 10, right? So this is kind of, we used the first rule, right? Saying that, okay, it's 20. It's 20 plus 30 equals to 30. Okay. Now let's think about this. I know that the x, the y, and the z should sum up to 12. Okay. But if you use the second rule, where whatever comes in the left has to kind of go out to the right, I don't know what y is or what z is, but I know that both of them, that this sum should be how much? So I know that the sum of y plus z should be how much? 10, right? Which leaves me with x being 2. Okay? So the x, well, let me leave this and just saying x is equal to 12 minus, then 10 goes here, you subtract 10, x is equal to 2. Okay? So this is the beauty of counting trees. You don't need, you kind of can get really calculations really fast without that much detail. I don't care whatever is in y or whatever is in z. It could be 8 plus 2, it could be 5 plus 5, it could be 3 plus 7, whatever it is, right? I know that they have to be 10. The sum of them have to be 10. If the sum of all the three, of all these paths here have to be 12, I I'm kind of left with, and only with, the possibility of x being 2. Okay? And I don't even know what kind of problem this is. It could be a huge problem with 30 elements that you would have to write 30 elements, and then, you know, oh, what is B complement? And then, oh, like, I don't know. But using the tree is really easy to kind of come by with this, okay? Questions?